Yo minasan, Rezzo stato, Rezzo fu samaritas. Fasto viviruka, electric power. Electric power is equals to U by T. U is electric energy consumed or created. So basically we have P equals to du by dt for small amount of energy created over small amount of time. But we can also write the energy, electrical energy as U equals to V, which is potential into charge. U equals to potential into charge. So if we write like that, it would be dq by dt. So that would be P equals to VI. So let's write that here. P equals to V by T, P equals to V by I. We have two methods of creating and using the electrical energy. First is source and other one is load. Source is where current is created, but what we need on theory is that it goes from current flow is flowing from negative terminal to positive terminal, or in other words, it's moving from lower potential to higher potential, which is done by the battery. So this is source. But what if it is load? When it is a load, then it will move from higher potential to lower potential. Current is approaching the positive terminal and moving out of negative terminal. In that case, it will consume the electrical power. Next, we have some examples where we just find out which is load and which is source. No need for that. Then we have electrical power of resistors. We know that resistor always acts as a load. So when it acts as load, it will consume electrical power. So there are some ways in which we can express this electrical energy consumed or used. So some of the methods are electrical power for a resistor. So there are some methods in which we can write or express the electrical power. So E equals to U by T is one way, another one is V into I. Another one using Ohm's law would be I square R or V square by R. These are methods in which we can express electrical power. If we are given electrical current and resistance, we can use this. If we are given potential and resistance, we can use this. If we are given only potential and electricity, we can use this. If we are generally given the electrical energy and also time, then we can use this. Let's write that here. Now we have an example. Before that, we need to know what is 1 unit. 1 unit is also known as 1 kilowatt hour, where 10 power 3 into uh, basically just remember we if we multiply all this, we'll get electrical energy. So that would be 3.6 into 10 power 6 joules. If you want to look at the derivation, you can look at here where they have multiplied 1 kilowatt into 1 hour, 1000 watts into 3600 seconds. First off, we have an example where a light bulb rated 100 watts and 220 uh, 100 watts and 220 volts is given. We have to find its uh, resistance, and we have to find its current current when voltage is 110. And last but not least, we have to find power when 110 volts potential is across it. So here we are given potential and power. So we have to find resistance, which formula has that V square by R here. So 100 watts equals to V square or 220 whole square by R. R equals to, if we want to square this, we have 4 by 100. 100 gets cancelled. R equals to 484 ohms. That is our first answer. Then we have I when we are given 110 volts as potential. Then what do we need to find? We don't have, we have current, we have voltage. So we have to just find current. But we already know resistance, so we can use I equals to V by R. V equals to 110 actually. And then we have 484, 11 forza, 11 forza. Yeah, that's right. So 44 times 2 into 2, 2 5 are 5 by 22. Then we have to find power. Now we know I, we know V. We can use VI. V equals to 110 into current is 5 by 22. So 11 twos are 2 fives are 25 watts. That's our power. Yeah. 25 watts. Next up, we have battery. We have battery, its load and etc. So first of all, what is battery? Battery is source from which we can get electric power. Then we have battery. So basically, a battery represents flow of charge, but uh, it may act as both source, not both at a time, but it can either work as source or as load. So if it works as a source, it will maintain source or load, it will maintain a constant potential difference across it through which allows the charge to flow and allow for current to exist. So basically, battery provides constant potential difference to flow the charge. Uh, if we see uh, a battery, it does not come without resistance. So it has some internal resistance, which we call as internal resistance. Uh, it will be dependent on the battery's the it is dependent on battery separation between the plates, and it is also dependent on how much bigger the area of the plates is. It is also dependent on uh, uh, inversely proportional to 1 by temperature, and it is inversely proportional to concentration. So basically, if we raise concentration, area, or area of the plate, or the temperature, in case of liquid batteries, raising temperature generally means uh, the ions will move faster. So that's also a point by which it is it is governed. We do not need to write all this, so it's okay. Next up, we have representation of a battery. For an ideal battery, the internal resistance would be zero, and for a non-ideal battery, it would be non-zero. For an ideal battery, we just write like this, but for a non-ideal battery, we would also represent a small resistor here. It represents R, its resistance is R, and it denotes internal resistance. Now, we'll come for electromotive force. It is actually not a force. It represents work done by battery to move charge from one plate to another. Or you can write U by Q, work done, right? W by Q, or we know that is U by Q. So it is the work done per unit charge to move it from one plate to another. EMF. Next, we have battery rated. So what is battery rated? It is just U by Q. Uh, Battery is rated. How we are telling how it is rated. So we can write in terms of kilowatt hour. We can generally write it as kilowatts into some time unit, which is hour, second, something like that, to convert it to joules. So here we are writing like that. Next up, we have battery as a source. So here, battery is acting as a source, and we are writing potential difference across the terminal, how it will change. So basically, if its EMF is E and its internal resistance, if we consider it as non-ideal, if it is R, and if current comes from a lower potential to higher potential while coming from here to here, if it moves from negative terminal to positive terminal, it would gain, if the potential here was zero, then it will be E minus IR, because here resistance takes away it consumes some of the electrical power. Next up, we have uh, we also have how much power we have consumed. So here P consumed, converted would be du by dt, or I P heat, power used for heating would be I square R, and then power output would be E into I. E here generally was how we had written for VI. Here we are writing EI because of electromotive force, and it loses this much energy. So potential would be E minus IR, but if we consider this is V, so we know that E is equals to V times I, so it would be EI minus I square R. Now then, what is short circuiting? Short circuiting is when we are attaching a non-resist a wire with no resistance in a circuit so that current through it, potential across it would be zero and no current will flow. So basically, if we take a circuit and we apply like this, here also zero, here also zero. So there would be no current. It's like, I don't know what it is. It's just called as short circuiting when two points are connected by a zero resistance resistive wire, creating VA to VB. So, and if we see resistance is zero, uh, resistance is zero, and the voltage across it is also potential across it is also zero. So electric current across it would be V by R. So R 0 by 0. It is not defined. It does not mean infinity. It is 0 by 0, which can be any value. So we'll use this point to find out how much current is flowing here or here later on. We also from this, we also find out that EMF is the EMF is the potential difference across the terminals of a battery when no current is flowing through it. So it is basically how much it can move without when without any resistance. Next up, we have some examples on this. This is internal resistance. This is electromotive force R, which is acting as a load here. This is resistor. So we have to find the current in the circuit, potential difference across the load, and we also have to find the rate at which the CE is converted by current electricity is converted by battery. So let's find out, and also power lost by heat, lost in heating the battery itself. So how much heat is lost by battery itself? First up, we have to find out uh, current in circuit. I equals to what? Next up, we have to find V equals to what? Third one, we have to find a rate at which is basically power of battery. Battery's power. And lastly, we need power lost by battery. Only battery, to be precise. I here would be uh, first E equivalent is same, but R they are connected in series. So I equals to E by R plus R, and then V equals to what is V potential difference across the load. Here across the load, if we consider it zero here, will current direction is mentioned, but it is from here to here. So if it goes from here to here, then if it comes here, it is E minus IR. So potential across it is E minus IR. I small r. Second one was that, and then find the rate at which the C is consumed by the battery, current electricity. So P battery will use V into I, or here V is E minus IR into E by R plus R. Am I right? Am I right? Am I right? No, I am not. Is E into I. We are not considering the resistance here. Damn. That is E squared by R plus R. Next we have power lost by the battery. It is P lost equals to I square R. That is E square by R plus R whole square into R. Okay. We are also told to find out P out by battery, how much output power we are getting by battery. That would be the same. That is I square R. P battery is same, right? We have found. Well, anyway, we have to find out, so we will. Here it would be internal resistance I square R. But in total, we have to find, if we have to find, then we'll write output is equals to E square by R plus R minus E square R by R plus R whole square. So basically what we are doing here is that we are seeing how much the battery is producing and we are removing how much it has consumed. So here it is how much it has produced. Vi, this result we are using here, E square by R plus R minus E square R by R plus R whole square. This is from here, P lost I square R. But if we look at it as a whole, it's just I square R. So E square by R plus R whole square. So that's that. Now we'll see efficiency of a circuit. In this question itself, we have to use it. So efficiency of a circuit is denoted by Y. It is how much it has given output and how much it has consumed into 100. So in this question, it is in this question, let us write that one first here. P out by PB into 100%. Yeah, Y%. We are asking. We'll use that. 5% is equals to, here P out is I square R divided by how much it has consumed. How much only the battery has consumed is E into I. I say I cancel, and I would be E by R plus R into R by E. E cancel. So this is into 100% into 100%. So this would be R by R plus R into 100%. That's, and we also have to know that Y value will always be less than or equal to 100%. If resistance increases, internal resistance increases, the Y value will decrease. Next, we have there are some uh, we have some inferences about the same question. They have made it super difficult. R1 R2 equals to R square. So they've made a graph and all. It's mostly advanced stuff. So it's okay. So basically what they have done is that in this previous discussion of question, we had come to the conclusion that P total would be P square by R plus R whole square into R. So what for what value of internal resistance would it or the uh, resistance would the P be max? So they differentiated in terms of R external resistance, and we got that if R is equal to R, then P is P max. So P max equals to 2R 4R. R C R cancels, so E square by 4R. That's our maximum P output, P max. And later they have modified the formula of R1 plus R2 and all, and they have gained this formula to plot the graph. R1 into R2 is equals to R square, and the maximum this is the maximum value of that graph. Now we will do a question on the short circuit part. Here we have attached a 6 ohm battery, 6 ohm resistor, external resistor, and they have also mentioned the here a general common sense is that whichever battery has more potential would dominate the circuit. So if this is 30 volts and this is 28 volts, it is very common to know that 30 volts would dominate over 28 volts and it would push charge like this. So when we have applied this short circuit, it would be 0 and 0. We can't say what the current is, but we can because we have a battery and a resistor. So how much it will push would be current in this circuit, and how much this will push would be current of this part of circuit. So here I1 if we take and this is I2, I1 would be this is 6 volts and this is 4 ohms, not volts, this is ohms. I1 would be V by R, so 30 by 6, 6 5s are 30, so this is 5 ampere. I2 would be 28 by 4, 7 ampere. Next, we have arrived at the most interesting part of this uh, KCL. KCL, it is junction law, Kirchhoff's circuit current law. So, junction law, in which uh, the sum of all current uh, leaving the junction would always be zero. So I1 plus I2 plus here it is arriving. If it is arriving, you have to make it leave by adding a negative. I3 equals to 0. So basically what we would write is for a circuit, delta I equals to 0, not delta, sigma I equals to 0. So I out, sorry, I out, sigma I out would be 0. Now we will solve some examples to know it more. Example, in such type of questions, we generally have to find the if the question is find current across the resistors, external resistors. Here 100 volts, 60 ohms. This is 40 volts, 30 volts, 20 volts. This is 5 ohms. This is 10 ohms. This is 26 ohms. So what we basically need to do is, if we consider this as 0, all these would be 0. And if we consider this 100, 100, 100, we can find across this one, which would be I equals to V by R. So this is, if we consider I5, V by R, 100 by 5, 100 minus 0 by 5 equals to 20 amperes. For this, we'll use the going above the circuit, above the battery and below the battery. If we come below the battery, potential will decrease by how much potential it already has. 100 minus 20, at this point it would be 80. 80 minus 0, so 80 minus 0 by 10 equals to 8 ampere. I3 would be here, the battery is in reverse, so 100 plus 30, so 130 minus 0 divided by 26, 13 to 26 to 5 ampere. I2 would be, if we take it here 0, say if we come up at this point, it would be 40 volts, so 100 minus 40 by 60. 100 minus, this is 1 ampere. And for I1, there is no I1. We messed up with the numbering system. So that was question number 1. In the same way, but this time we have a different type of question in which we are properly using the junction law. Here, that was a basic question previously. So now we'll use that knowledge here. Here we have 200 volts. This is also 200 volts. This is 400 volts. So we'll take the largest one. This would be 0. This would be 400, 400, 400. This is 600. Then this would be 400 plus 200, 600. We have to find out current through each wire here too. So we have to take across the wire. So we don't know the potential here, or else we could have taken already. So this would be considered as X. So for this resistor, we need to find out the, we forgot to write the resistance. So that is 4 ohms, 4 ohms. This is 8 ohms. So for current, we will use junction law. So x minus 0 by 4 for this one. Is x minus 600 by 4 for this one. And here plus x minus 600 by 8 equal to 0. So I make it 8 by adding multiplying by 2, 2x, 2x, 5x, 5x minus this would be 6 is 18, 0 is equals to 1000 by 5, 5 so 50, 6 are 30, 360 volts. So now we'll just substitute it again. 360 because I take this as 16. So here we'll solve it later. We can solve it, right? We just need to find this, substitute it in each of them, and find out the current in each resistor. In similar fashion, we have two other questions. In other one, the example 4, we can shift the battery with the resistor if they are in series. That's a funda. Now we have Kirchhoff's voltage law. We have another question. Let's solve that one too before we move on to next topic. I don't want to make the video long. This is 5 ohms. This is 50 volts. This is 10 ohms. This is 20 ohms. This is 100 volts. So basically, we just need to find out current in each wire. So we'll use this. Here 0, 0, 0. Then this would be 50. And if you go here, this is 100, 100. We don't know this point. If we know this, we can find this, this, and this. Let's assume it x. So x minus 100, x minus 100 by 20 plus x minus 50 by 5 plus x minus 0 by 10 will be 0, 5. This needs 5, 4 are 20, so 4x minus 200 plus this needs 2x, x minus 100, 4, 5, 6, 7, 7x, and this is minus 300. It's equals to 300 by 7 volts. Step back in each of them and find out current for each wire. Now we are going to start with KVL. KVL, which is Kirchhoff's voltage law. KVL, it is also known as loop law, my funda. So loop law, which is what I want to call it. No, it's already called as loop law. So loop law. So basically here when we go in a closed circuit and arrive back at where we were in a loop, then the sum total of all the potentials could be 0. Let's see that with an example. Ten ohms, 2 ohms, 3 ohms. This is 5 ohms. This is 100 volts. So if we go like this is 100, this is 100. We are given, we have to find current. Finding current is best for that to find current. So if we assume current to be I equals to what? So 100, 100 minus, as it acts as a load, this is 100. First we'll write 100 plus 100 minus 10i plus 100, 10, that's one, so 100, then minus 10i minus 10i minus 2i minus 3i minus 5i. So this is 5, 8, 10, 10 and 10, 20. 20i equals to 100. So first is 10, 0, 0, cancel. I equals to 5 ampere. In similar fashion, we have another one. I think it needs no solving. Let's just jump right into example 3. Example 3, in it we have this is 8 ohms, 100 volts. This is 2 ohms, 3 ohms, 5 ohm, 5 ohm. This will be 200 volts. This would be 200 volts. This is 2 ohms. So basically, we have to find out current in each wire. So for that, we need two circuits, I guess. So this one, let's see, have written later on, I guess. In this question, basically, we have current flowing from here to here and here to here, because if we see it, this is giving us common potential, and these aren't actually parallel because they have same potential across their junction points. So this is I1, from here it is I2, this is I1 plus I2, that will flow here and then they will split again. So we'll need two equations to solve this. So we'll first apply the KVL here outside, then again inside. So first outside, let's start from here, 100, then we are going towards the load. So it would be minus 8i, then outside, right? So we are going approaching opposite to the direction of the flow of current and opposite to the resistor. So that would be plus 2i2. Then we have minus 200 plus 3i2. Then we have minus 2i1 equal to 0. Then we have, if we go in the inner circle, that would be 100 minus 8i1 minus 200 minus 5 into I1 plus I2, and minus 2I1 equal to 0. And 10 I1 plus 5I2 minus equal to 100. So that we did, so 5, sorry, 5 2s are, so 2, 5 2s are 10. This would be minus 5I1, so 5, 8, 7, 2, so 14, 15. 15i1 equal to plus 100 And this would be I2 would be minus 5 I2. We bring it over here plus 5 I2, I guess. Yeah, I'm right. That would be if we take 5 common, 5 to 13, 5 is a 15, 5 to is a 10 plus I2. Now we have 2 I1 plus I2 minus 20 equal to 20, and then we have 3 I1 plus I2 equals to 2 3 I1 plus I2 equal to minus 20. If we subtract these, we have I1 equal to I1 equal to minus 40. I1 equals to minus 40. Oh shit, I messed it up. I just missed a minus point here from here. So that would be minus minus plus. So this would be 5. 5 eighths of 40. I1 equals to minus 8 ampere. So if we put that back into the original equation, if we put it here, I2 equals to 20 plus 2 times minus 8 because I2 to the 64 ampere. That's all. Thank you.